This podcast is brought to you by HEC Paris.
Thank you very much to Laurent and Veronica for inviting me. It's a pleasure to be here back in Paris. This is joint work with Julio Cacho-Diaz, who is a PhD student at Princeton, Tom Hurd, who's at McMaster in Canada, and Roger Lavin, who is at Tilburg University. What we're trying to do here is try to propose a reduced form model that in some sense describes or at least captures some of the aspects of what we've observed during the recent financial crisis. So in a sense, it's in the same spirit as the work that Peter Phillips proposed this morning, where he had also a reduced form model of what asset prices did during the crisis. We have a different tack on this, but fundamentally it's work that is in the same spirit. It's reduced form in the sense that we are not trying to explain why things are doing what they're doing, but we are simply writing a model that describes things that appear to be realistic to us given what has happened. And in our case, our primary focus is on trying to generate crises with the type of frequency that has been observed empirically over time. And clearly, if we use the standard models we use in finance, so certainly models that are driven by Brownian motion will not be able to generate the kind of crazy asset returns that we observe. And even, as you will see, models that are driven with jumps will not be able to give that to us. And you will see why standard jumps won't do. So what I'm describing is a model for contagion, which is an area, for those of you who are familiar with what's known as international finance, is an area that has seen a lot of activity over the years. There are both theoretical models for this. You see some of them here, as well as a lot of empirical papers or econometric papers that have worried about questions such as, what is truly contagion? How do you distinguish contagion from spillovers? How do you know through which mechanism these things? How do you test for contagion? So there's been a lot of activity in this area, as I said, largely in the context of international finance. What we're going to do is try to write, as I said, a descriptive model that generates the kind of things that seem to us to be the salient features of crisis with contagion. Now, clearly, we're going to need jumps for this, and because, as I said, just a Brownian motion just won't do it on its own. Now, once you have jumps, what we want a model where the fact that you have a jump somehow raises the probability that you will see more jumps, both in time, because a lot of crises do evolve a bit like earthquake aftershocks. Earthquakes are very rare, but once you have one, chances are you're going to see a lot more shocks in the future. Not necessarily in the same direction. In the case of crisis, things sometimes rebound and so on. So in the time dimension, you want to have that aftershock effect. And cross-sectionally, you also want to have what is usually called contagion, which is the fact that if Wall Street decides to drop by 10%, chances are European markets, Asian markets, when they reopen the next day, and so on, will also move in ways that are commensurate with what has happened on one of the markets. And sometimes, of course, contagion can go in different ways. So what we want to produce a model that generates both of these aspects, the cross-sectional contagion and the time series dimension of it. Generally speaking, when people talk about contagion, they talk about the cross-sectional aspect. That's what worries people. People are worried about contagion to other markets, contagion to other asset classes, or contagion to different equity markets around the world, different regions of the world. So the time series is something that is usually less emphasized, but when you look at the data, there's very clearly evidence that the arrival rate of jumps goes up significantly in response to recent jumps. So that there is variability that's quite predictable. While the jump themselves are unpredictable, their arrival rate is actually. So what we're going to do is we're going to use jumps, but we're going to use jumps that are different from Levy jumps. So Levy jumps will generate IID increments, and with IID increments, clearly a large increment now is not going to predict a large increment tomorrow, which is exactly what we actually want to capture in this case. We want to capture this time series dependence in the arrival of the jump. So we're going to have to move away from Levy processes. Even though they're very nice, they're very convenient, we're familiar with them, you know, we like the Poisson process, and so on. So a lot of the intuition that comes from this is quite familiar, but they won't do the job in this particular instance. Instead, we're going to use a different type of jumps that are called Hawkes processes, after work that Hawkes did a long time ago now, in the 70s, and that was originally proposed to model epidemics. The reason this was a model for epidemics is that if you think about what happens when you have an epidemic that propagates in a population, the likelihood that you get infected depends upon the amount of people who are infected around you. I think that's a rather, you know, if you had to sort of think of a first order determinant of what causes an epidemic to go on, that would probably be it. It's a model that then, again, perhaps not too surprisingly, but by researchers in Japan, was clearly picked up as a model for earthquakes. And earthquakes are sort of interesting in the sense that they also give you these dual time series. I've mentioned aftershocks as one example, as one motivation, but also the cross-sectional contagion, which is less emphasized in earthquakes, unlike finance, where in finance we tend to emphasize the cross-sectional contagion and discard the time series dimension. In earthquakes, you usually worry about the time series dimension, but there is also a usually actually beneficial cross-sectional contagion, in the sense that if the fault breaks here, it appears that it's less likely to break nearby. So that actually a jump somewhere cross-sectionally decreases the likelihood of you observing a jump nearby. It's kind of the reverse of what we tend to observe in crisis. So in earthquakes, that has been picked up. Models of this kind have also been proposed recently to model defaults in credit derivatives by Kei Giseke, who's done a lot of work along the lines of trying to understand how in portfolios of CDOs that are made up with lots of CDOs, or even if you just take a CDO itself that's made up of lots of different defaultable instruments, what has been observed over the last crisis is that default in one instrument, even though the whole theory of sort of trenching and pooling was based on the idea that those were perhaps not independent risks, but certainly not heavily dependent risks, which would, you know, then generate benefits from pooling. What has been observed is that there was a lot of contagion within the portfolio. So you had mortgage-backed securities that would go very quickly from 0 to 90% default, for example. Okay, despite what sort of one would have expected. There's also sort of a nice sort of cute paper that I saw recently that looks at the viewership of YouTube videos and looks at the ones that make it up to the top of the most viewed list. And that looks at that as sort of a proxy for what are called viral processes on the internet. Which, if you think about it, function largely like epidemics. The likelihood that you view something on YouTube is influenced by how many other people have actually viewed it. And then once you have that, you sort of tend to have a chain reaction. Because, you know, you view it, it makes it up to sort of the top viewed list. If you use an iPhone, for example, most of the news apps on the iPhone would have a most popular or most viewed button that would automatically show you what other people have viewed. So that's a sort of a phenomenon that's called self-excitation, in the sense that once things get excited, they tend to perpetuate. And that's exactly what Hawkes processes will do for you. So we're going to write a model where the jump part is going to be Hawkes processes, just like what I've described. And then for the rest of it, our model is going to be very classical in the Merton tradition. So you're going to have sort of an expected return, you're going to have a stochastic volatility, and then you're going to have that. And then the question becomes, then what can you do with it? And how can you estimate it? And that's what I'm sort of hoping to walk you through in this talk. So the key features is that you're going to have sort of jumps, but you're also going to have this amplification phenomenon that comes from the self-excitation. And so the model is going by construction to generate the kind of successive jumps across world markets or asset classes that tend to be observed in crisis. And it's going to produce clusters of jumps. There's a large literature that has documented that jumps, just like volatility, tends to be clustered. With work by people like Boleslav, Tauken, and others who have studied clusters, usually in volatility, but they've also looked at clusters of large deviations or large increments, so jumps, and you tend to also find a lot of clustering. And you will see that this is quite important in the data as well. So, for example, here's what was sort of observed in the data. This is sort of from 2007. This was a drop in the Chinese stock market. These are 5 trading days. Each color is for different regions of the world, as represented by the MSCI World Indices. And this is sort of a cumulative drop of about 10%. And what you see is basically that the world markets tend to move together in sync, even though this was driven by some changes to the regulations for trading and owning stocks in China that presumably should have little influence on what the Latin American equity index does, for instance. And yet that's not what you observe. Just like you observe large moves, these are multiple standard deviations in terms of daily variation, and yet you observe many moves in successive days, some of them being rebounds, by the way. But if you think about a jump of this magnitude as occurring perhaps once a year, it would be relatively unusual to see moves of this magnitude in 5 consecutive days if you really had IID, if you truly had an IID driving process behind this. A more extreme example is what happened about 2 weeks after Lehman Brothers, when you looked at those large jumps in all asset returns. Now the scale is much more dramatic. Now you're going from this is from the top of the graph to the bottom of the graph. This is a drop of about 35% in world markets, and you have exactly the same story across a few trading days. Another example, more recent, is what happened to Greece over the past spring. So this is Greece from 2000 until this summer. And that's an example that I like because you actually have a sense of observing the jumps separately from the asset returns. You observe the jumps if you think that downgrades and upgrades by the rating agencies are what is actually the main driver, certainly in the recent period of the Greek. In this case, you have 3+, which are Greek, Spain, and Portugal. What you say is that these things are certainly self-exciting. Cross-sectionally, those countries tend to be upgraded and downgraded together, but also once they start getting downgraded, they start getting downgraded at sort of a fast clip. So you see sort of both the time series and the cross-section there at the same time. And if you look at the resulting asset returns, this is now not the full period from 2000, but this is just April and May of this year when Greece, Portugal, and Spain were really very much in the news. I mean, it's hard to imagine asset returns that are more correlated than this if you look at them over that particular period. Okay, the full sample, you see sort of the same type of story. Okay, so what does the process look like? For the jump part of the process, what we have is something that is a point process. So in fact, we have one for each region or asset class. And what you have is you have an intensity, lambda, for the region L, which is a stochastic process now. And what makes it self-exciting, so this is the probability, just like in a Poisson process, the probability that you'll have one jump is lambda dt, but that lambda is going to be stochastic. It's going to be stochastic, but it's also going to be path-dependent. It's going to be path-dependent in the sense that what gets lambda up are recent jumps in the asset in the same jump process. So whenever the jump process goes up, whenever the jump process jumps, whenever it's 1, then this lambda is going to go up by a quantity d. And it's going to go up in response to not only its own jumps, but also jumps in the other regions. So DJL doesn't need to be sort of the same as djj or dlj. Okay, things could be asymmetric, or the diagonal excitation could be higher than the off-diagonal excitation. And then over time, these things are going to get smoothed out or averaged out, which is the role of that integral here. Okay, so we're going to have those jump intensities. They're going to be stochastic. They're going to depend upon the path of the past jumps in its own region and in the other regions. Now, a special case that simplifies matters is if the averaging takes place in an exponentially decaying way, so that recent jumps matter more to excite the jumps tomorrow than jumps that took place in the past. And if actually there is enough, if there is enough decay relative to the amount by which things get self-excited, you're going to get, meaning that this condition is satisfied, then you're actually going to get a stationary process. And if you include the intensities in the state vector, it's actually a Markov process, meaning that given the intensities, things are no longer path-dependent. And what you have is you end up in that situation with a model that looks like the drift of an Ornstein-Uhlenbeck process. So it looks like basically a linear mean-reverting drift. So intensities mean-revert to a certain level lambda, but whenever there is a jump, intensities jump by what is now a constant parameter, delta JL. So there's a jump in region or asset class J, then the intensity of asset class or region L jumps by delta LJ, and it jumps, and then it sort of mean reverts at a speed alpha L. And so that's sort of that's sort of probably the simplest model one could write within that sort of class, and that gets a sort of a stationary process. You realize that if you didn't have the mean reversion, then this would explode. And this wouldn't explode mildly, this would actually explode quickly, because if you have a jump, then the intensity goes up, then you get more jumps, and the intensity keeps going up and so on. So clearly, you need to have enough mean reversion relative to the degree of excitation to get stationarity. So this is what an intensity looks like. Things go up, there's a jump, intensity goes up, then they mean revert, but then intensity are higher, so you're more likely to see a second jump. Then once you've seen a second jump, the intensity is even higher, so now you're more likely to see a third jump, and so on. Okay? So in a way, there's a feedback element that comes into this that plays the same role for jumps as what arch or gauge does for volatility. If you think about what an arch model does, in an arch model, you also have a feedback from returns to volatility in the sense that if you have a large return, that generates a large volatility because volatilities depend upon squared returns in an arch model, then you're more likely to observe large returns again if you have large volatility. But then you have mean reversion that makes this whole thing stationary. Here we have the same thing, except that the channel for the feedback is through jumps, in the sense that if you have jumps, then in a self-exciting model, you're going to get larger jump intensities. If you have larger jump intensities, you're more likely to see more jumps. And as you see more jumps, then mean reversion counteracts that and makes the whole thing not explode. Okay. So to this jumps, we're going to add a drift and stochastic volatility. So in a way, what we have is what one might call a Hawkes diffusion process. Just like there are basically standard Poisson jump diffusion processes, this is a bit like a Hawkes diffusion process. So you have the Hawkes process for the jump part, and then what we're going to do is we're going to add sort of the classical rest of it, sort of the usual, again, drift and diffusive part. Okay, so this is what the model looks like. These are log prices, so changes are log returns. The risk-free rate, an excess return, a stochastic volatility, a Brownian motion, and then you've got the jump part. And the jump part, again, gets yourself excited, and so on. There's a random, since the jump is always by 1, there's a random jump size, which is Z, and N is a self-exciting process. That's the equation. Okay, the first question I'm going to ask is, how does one estimate a model like this? And we're going to estimate it on international equity returns, and we're going to estimate it by GMM. So we actually get the first 4 moments of the process explicitly, again, despite the self-excitation. Now, in order to get moments, I told you this is a stationary Markov process, but it's a Markov process with a large state space. So given that it's a Markov process, you can sort of see that it's possible to get probably 1 step ahead transitions. And it turns out, yes, you can indeed get conditional moments one step ahead. But they have to be conditioned on the full state vector. And part of the full state vector is latent, in particular the intensities. The volatility is also, but in particular the jump intensities. So what we have to do is we have to condition down, after we do the initial calculation, to effectively integrate out the unobservable intensities. So that's the result of the calculation I'm going to show. I'm clearly not going to show you the calculation, but the result is basically are the moments of the returns conditioned only on past returns, but not conditioned on intensities, not conditioned on volatilities. So this is the moment where you have effectively integrated out the part of the state vector that was latent. Okay? So this is what the moments we're going to look at are returns, variance, skewness, and kurtosis. The reason we need to go all the way to moment 4 is because we have jumps. So if we want to be able to learn anything about the unconditional distribution of the jumps, we need to go beyond the variance, because the higher order moments are going to pick up the jump components. And then we're adding two moments that are there to pick up, to the extent that it's present, first, the cross-sectional contemporaneous excitation. This is what these moments are going to be. These are basically covariances of returns, contemporaneous covariances between returns in asset J and asset K, but also something that is a clear departure from having IID returns, which is an autocovariance of returns. And they're not just autocovariances in the sense that this is not K equals J necessarily, but since you can have contagion over time, both cross-sectionally, you can have contagion from K to J that propagates over time as well. So these moments would basically be zero in the absence of any self-excitation. So these moments are there because each one of them sort of isolates one element of the model. Okay, let me show you what the moments look like in the one-dimensional case. So this is the simplest model within that class. It's a univariate model, so there is only time series contagion, since there's only one asset class. Since there's only one asset class, there cannot be any contagion to any other market in this model. So these are returns. So this is a stochastic volatility. We're going to make that stochastic volatility be a Heston model. Okay, you can have as much leverage as you want between those two Brownian motions, but once you have those big jumps over a period of crisis, that is no longer a big element during the crisis, but it's there. Then you have jumps. So Z is the random jump size, N is the jump process, and of course what makes this self-exciting is that the intensity of this N is lambda here. It's mean reverting at speed alpha, as I mentioned, to some level lambda infinity, and whenever there is a jump, and the key thing, of course, what makes it self-exciting is that this is the same N. Okay, so it's the past jumps, it's what gets lambda up are jumps of the process of which lambda is the intensity. Okay, so basically whenever there are jumps in asset returns, then the intensity of future jumps in the same asset returns goes up. And it goes up by a parameter beta. Okay? So what do the moments look like? The only thing that is unspecified here is what is the distribution of the Z process, and the moments of the Z process, we write them as MZK. And this is what the moments look like, okay? So it's not particularly enlightening, except that I don't have time to tell you what happens at the first order, but clearly at the first order for the high order moments, it's the jump process alone that takes up everything. For the moment number 2, the variance, you get a mixture of the long-term volatility parameter, the variance parameter, as well as the second moment of the jump process. So if you're familiar with the high-frequency literature, the quadratic variation will mix effect from the continuous part of the model and the discontinuous part of the model, but higher order power variations of order greater than 2 will, at the leading order, be functions only of the jump or the discontinuous part of the model. So that's exactly the same thing that happens here, not surprisingly. As to the autocorrelation function, then it depends upon the self-excitation parameters, not surprisingly. It depends only upon the self-excitation parameters, because without that, returns would be IID. So if you go in this model and you kill the self-excitation here, then your returns become IID, and you would have no autocorrelation at all. Okay? Now, so we have sort of multivariate versions of this in the paper, and let me just go straight to what the results would be if you estimate a bivariate model. So the bivariate model we estimate is we have 6 world series, and we're going to estimate a model where bivariate with the US and each one of the other 5. Okay? So the reason for doing this is not Americanocentrism, although none of the authors are Americans anyway, but that's not the reason. But the reason is, as you will see empirically, a lot of the contagion needs to involve the US equity market. So contagion doesn't really somehow go from Latin America to Southeast Asia. There will be contagion only if it somehow transits through the US equity market. So it's sort of the culprit out there for transmission of crisis, in a sense. And what you find is you find sort of 4 plots on each one of them, which measure basically the autocovariance contemporaneously, going from one country to the other, and then going from the other country to itself to, so anyway, there's J to J, K to K, J to K, and K to J, okay? It's easier said that way. So you've got 4 plots, and what you find fairly uniformly in all cases with all regions of the world is that generally speaking, there's more transmission from the US to the other regions of the world. So delta to 1, which is the parameter that controls the extent to which the US market excites, so jumps in the US market raise the intensity of jumps in the other market, in the other regions of the world. That's usually the highest parameter, the highest of diagonal parameters. So delta 2-1 is higher than delta 1-2. You also have delta 1-1 and delta 2-2 that measure the degree of self-excitation. The diagonal parameters, which measure the degree of self-excitation, tend also to be quite high. So jumps in your own market tend to also raise the intensity of jumps, future jumps in your own market. Okay, let me skip this. Okay, now there are 3 applications, and I have 2 minutes, so I will do those 3 applications quickly that you can do. So this is a reduced form model, okay? So it's not meant for to try to explain why this is the case. So as I said at the beginning, all we do is we assume that this is the model. And then the question is, what can you do with it? So the first application is, well, if you face asset returns that are subject to this form of contagion, can you construct an optimal portfolio? And in other words, can you solve the following problem? If those are your asset returns, that's the same model except it's written in percentage returns instead of logs. But if you have this model and you have the same excitation and you're trying to solve the following problem, which is find the optimal weights that maximize expected utility of consumption with some discount factor, time separable, infinite horizon. So very much a classical problem. No other sources of income. Whenever you consume, your wealth goes down, and then the only source of income are your returns. Can you find the optimal portfolio? The answer is yes, at least in the log utility case. And I really think it's only in the log utility case, frankly, from everything we've tried. But at least in the log utility case, you can do it. Now, interestingly enough, despite the fact that this is log utility, you do not get a myopic solution. The jumps introduce non-myopia in the investor. And that's because the self-excitation introduces a delay in the Hamilton-Jacobi-Bellman equation. So the HAB equation is not going to be sort of get you the myopic solution that you would get with the normal scenario. And in particular, you see that the optimal solution depends upon lambda in all the different assets. This is sort of the classic physics notation where lambda L, J, L means the sum over all the terms that have sort of that index in there. So the optimal solution is time varying. If Z bar, the average jump size, is negative, you see that an increase in lambda causes you to decrease your asset allocation to all the risky assets. So that's exactly what you would get in a flight to quality, where if you perceive lambda to go up, then you run for the exit on every asset class in the world. And that's because you have cross-sectional self-excitation, because you know that if there's something bad happening here, that predicts bad things happening everywhere. Okay, tails and VAR, and that will be sort of my last application. If you ask yourself how big are the tails in a model like this, how big is the left tail? And let's suppose you're a banking regulator. Okay, and what you worry about as a banking regulator is the probability of joint losses in multiple institutions that you regulate, presumably. Okay, so you don't necessarily worry about one bank doing something stupid and losing $1 billion here or $1 billion there, but you worry about multiple financial institutions losing within the same period. And clearly, if you have a model where risks are largely independent versus a model where risks are self-exciting, you're going to get a very different answer if you do that sort of left-tail calculation. So I'm out of time, so let me just show you on the plot what happens. You have 4 different models here, and what you have here is a contour plot of the joint distribution of losses on 2 different, say, financial institutions. You can think of them as sort of being 2 banks. And what you see here is just the lower left corner of the distribution. So this is a contour plot. So it's a plot of the joint distribution from above, and this is the lower left quadrant of that. If you have a model with just Brownian risk, you can't lose money with Brownian, basically. You can lose money, but, once every 1 billion years. If you have independent Poisson jump diffusions, then you can lose money, but you're not going to lose money very often because over 10 days, you're very unlikely to get more than 1 jump, and you're also very unlikely to get a jump in both institutions together if you have independent Poisson processes. If you have correlated Poisson processes, which is the 3rd plot here, now you still are very unlikely to get more than 1 jump because those processes are independent over time. Now they are cross-sectionally correlated, so now you're more likely to lose a lot of money, both of them together, because if one loses, the other one is likely to lose, but you're only going to get 1 jump over 10 days. If you have if the thing is calibrated to get you 1 jump every 5 years, for example, then you're not going to get 5 jumps in 10 days, okay, with a Poisson process. If you have self-excitation, then all hell breaks loose sometimes, because once one starts to lose money, you're very, very likely to get this acceleration process. Okay, I'll stop here because I'm out of time.
Thank you, Yassine.
Please visit us at www.atc.edu.